This is Polarized Light Microscopy in Archaeology. In this lecture, we'll be briefly looking at mineral identification and paste studies. Now, what this is about is basically looking at in magnification at broken pieces of pottery in preparation for petrographic analysis. So here we have a piece of pottery, and you can see there are things in it, and these are the things we're looking at in the polarized light microscope. But as you can see, with the assistance of magnification, this is 30 times magnification, you can actually see those inclusions not in a microscope. Identifying them, however, is a bit harder. But it is possible, and certainly it is possible to characterize them if it's not possible to identify them. And so this is a part of what should be done on every petrographic pottery study before you start cutting up pottery. You need to sort the pottery based on its paste and looking at the inclusions with it with the hand lens. These are very obvious differences. This is like some sort of sigillata, red slipware thing, and these are like not. But it's a very obvious difference. But what you should be doing then is to be looking at these broken sections, looking for inclusions, and trying to say, oh, this has a lot of quartz in it, or this has a lot of, I don't know what it is, but they're black and they're very small. And like that. And so you can start forming groups, and it might be that only one of these is of this group, but that makes it a very important possible import. And so you'll want to sample that one and sample, some of all of the others and the exotic ones, which may turn out to be the same as the imports or the same as the locally made ones, and all the other odd things that you find in the paste study. And so identifying the minerals is a part of this, and there's a number of things you need to do in order to do that, apart from like looking at it in high magnification and poking at it in various ways. So in looking at pottery, and here you can see I've shown you this cut section before of a handle being attached to the body. You can see these would be two different fabrics. Hopefully if you did petrographic analysis of these, you'd find that the only difference would be the abundance of the inclusions. But if you did see these as separate pots, then obviously you'd want to sample each of these different fabrics. So you'd want to characterize the paste in the same way, with abundance, how much of it there is, how sorted it is, the grain size, the roundedness, and the mineralogy. So the abundance and sortedness, and the roundedness, you would work out the same way as you do for in the thin section. It's just it's very small, not like in the thin section. For grain size, there is a handy dandy comparison chart in your manual. And so essentially the folk grain size classifications, which we typically use, some of these big things, it's very easy to say, oh, well, that's like it's a millimeter across, that's coarse sand, or bigger than that is very coarse sand, or bigger than 2 millimeters grit. But finer than that, it's difficult to actually get down and measure it. So it's basically a matter of medium sand. You can barely see it, but you can see it. So it's less than 0.5 millimeter, but it's big enough to see. With fine sand, you probably need a hand lens to see it properly. It's going to basically look like someone's put salt and pepper in the pottery. It's just very fine material. Very fine sand, you can barely see it at all with a binocular microscope, so you're not going to see it without any magnification at all. Whereas silt, you can only see that in thin section. Okay, so these only go down to very fine sand, but they're about the same size of these ranges of inclusion. And so when you're looking at a broken piece of pottery and you're looking at the inclusions, you should be able to look at this and say, yeah, they're about very coarse sand size, or maybe they're medium sand, or I really can't see them very well at all. Well, I can see something, it must be fine sand. And maybe with like the hand lens, 30 times hand lens, I can see something. Maybe that's very fine sand. So you should be able to roughly, and all of this will be a rough definition of each fabric. You're not going to have the same sort of precision you have with the thin section here. It's just a matter of doing preliminary groups. But by doing that, extending the analytical polarized light microscopy study to the entire ceramic corpus of the site or the corpus that you're working on. So identifying the minerals is based on sight, the shape and the color and the luster and the cleavage and the parting and the fracture and the diaphaneity and tests. The number of tests we do, there's hardness, the streak, magnetism, sectility, acid reaction. Okay? So shape, going through what you can just see by looking at, these basic shapes are things that we've already covered. Just being able to describe an inclusion is also important in the thin section, and it's just as important in a broken section, where you're just looking at, oh, it's filled with like, acicular inclusions. I have no idea what they are, but this group of pottery is filled with acicular inclusions. This one's filled with platy inclusions. And so that would be a part of the characterization of each group. Luster, the luster of the inclusions. Luster is a slightly more pretentious term than just saying it's shiny or dull or something. So there's metallic. So you will have metallic luster inclusions, not very likely. Vitreous, more likely, of course, because glass is vitreous. I know glass is obviously vitreous. Quartz is vitreous. Pearly, this is it's like talc. Earthy, this is earthy looking. And silky, looks like gypsum. Adamantine, very unlikely, these are diamonds. And things like that. So, and you have cleavage. You remember cleavage? We talked about cleavage. And when you're looking at teeny tiny grains, imagine this is like really teeny tiny, you will see the cleavages on them. And you will have perfect cleavages. And you will have poor cleavages, which this isn't, of course, is a perfect cleavage. And you will have partings where it sort of breaks apart like that. And that'll create blocky shaped inclusions. So I don't know why all my videos are upside down when they start, but so this is what you're looking for. You're looking down at your hand lens, and you see that some of those inclusions have these little flat. Let's go back. Flat, shiny surfaces. So that tells you that inclusion has cleavages. Might be a feldspar or calcite or something like that. So fracture. There are lots of different types of fracture, only two of which are particularly useful. There's conchoidal fracture, like this in quartz or this in obsidian, and you have everything else. So there's uneven, hackly, and all the sort of thing. I talk about this a bit in the manual. It's more useful for talking about breaks in pottery, if you can define what uneven, hackly, or even etc. actually means. But for teeny tiny inclusions in pottery, it doesn't work so well. So conchoidal, this is supposed to look like a shell, you see this? That's what this is based on. So if we look at this, this is a piece of quartz. It's a big crystal of quartz, actually. And you can see this, you can see through it, which is also another property. See, there's my finger. But you can see here that conchoidal fracture, very characteristic of quartz, for instance. So, looking through it is called diaphaneity. Can you look through it? Is it diaphanous? And so, transparent minerals are things you can see through. Translucent, you can see into. And opaque, you can't see into it at all. Yeah. So, things like metallic minerals you can't see through at all, but also a lot of other things. And you have hardness, which we measure by the Mohs scale. So that's like, not this one, not this one, but this one. So not Larry, not Curly, but Moh. The Mohs scale, although it's actually not this guy, it's this guy, Friedrich Mohs, who come up with his hardness scale in 1832. So in this, you have all these minerals which define these degrees of hardness. Typically, talc is gouged by fingernail. 2 gypsum can be scratched by a fingernail, not gouged but scratched. Calcite, you can gouge it out with a blade. Fluorite, you can easily scratch it with a blade. Apatite, you can just, you can scratch it with a blade. Whereas orthoclase, you can barely scratch it with a blade if it's a good one. This actually doesn't work for teeny tiny things in pottery, and so I have come up with the pottery version. So what you want to say is this inclusion may be very soft, soft, hard, or very hard. So soft being, you have one of those little pointy things I showed you earlier on, and you poke away at it, and you can easily gouge it. So it's 3 or lower. Soft, yeah, I can scratch this. About 4 to 5. It's hard, so, if I work at it, I can, scratch this, so maybe about 6. Or very hard, as in, yeah, no, I'm not going to scratch this. So that's where you need something like this little thing. See, there's a little bit of gypsum, and you want to just scratch at it with one of these. So that's a useful thing to have in your field kit, which, that was the field kit. So, another useful thing you can do is called streak. Here we have an example of 2 mineral streaks, and this is done on a little white tile. So that means you have to carry little white tiles around with you everywhere, and you use the mineral to draw on it essentially like a crayon, and it comes up with a color which is very characteristic. And to show how this actually works, this is pyrite, and it has a black streak, whereas this mineral, actually this is a tile, the mineral which will appear any second now, looks a lot like pyrite and is in fact also iron sulfide, but it has a brown streak. This is because it's called marcasite. It's a different mineral. Here's another mineral. What's this? It's quite soft, and look at that streak. It's sort of dark grey, isn't it? So any idea what mineral that is? This might give you a hint. I have a piece of paper to be hanging around, and you can see you can draw on it. So that should tell you that this is actually graphite, the same as you get in a pencil. And magnetism, these are magnetic things are actually easier to test. If you have a little black thing in there, or possibly red thing, and you knock it out and you poke at it with a magnet. This is a high power magnet, and so if that little thing you just kicked out of the piece of pottery does that, it's magnetic. So that would probably mean it's magnetite. And I couldn't find my bottle of 10% hydrochloric acid, so I couldn't show this to you, but this shows it well enough. Acid reaction, it's worth having a little bottle of hydrochloric acid, dilute hydrochloric acid. And then if you have these little white things in the pottery and you put a teeny tiny little drop of this on it and effervesces like this, as in big bubbles and that sort of thing, it must be calcium carbonate, calcite or aragonite. Okay, so this is what shell is made of, aragonite. Calcite is a common mineral of things like limestones. So those little white, possibly somewhat soft things, you put that on it and it fizzes, then that pottery is tempered with calcite or aragonite. If it doesn't, or only effervesces slightly, if you warm up the HCl, it may be dolomite. So this is quite a useful technique, which I couldn't do a video of because I couldn't find my bottle. So sectility. So again, this is something you need to try. Basically, there is things which can be bent, are sectile, which is mica. Only mica you can do this to. And things which aren't sectile or brittle. So it's non-sectile, it's basically not sectile. So what this looks like, here we have the two types of mica, two main types of mica, biotite here, and muscovite, the white one, and the one with all the iron and magnesium in it, the biotite. And so you can see the perfect cleavage on here, a nice shiny cleavage. See how it breaks into these bit flat sheets. This isn't what the original crystal looked like. So now I'm looking for a bit that I can sort of flake off a bit, and no, that won't do. Somewhere on here. Hang on, what's this? There, see how it bends? So only micas do that. I should have done that for a bit longer, but never mind. So there you go. So now just briefly talk about a few minerals it's worth knowing. So one of these is quartz, which you know in thin section of quartz now. So it says here colorless. They mostly are colorless. It's very hard. There's no cleavage, so you're looking for a conchoidal fracture. It will be transparent, translucent, and it is vitreous, like glassy. So this is actually upside down. I don't know why the videos are upside down in here. But this is quartz, so it's not always colorless. These are all quartz. That was quick. There you go. Okay, let's go back to that. See, it's upside down, but all these are quartz. Feldspars, also quite common inclusions. Dirty white or colorless, quite hard. They will have cleavages, so those hard white things in your pottery that have these cleavage fragments going on, they're probably feldspars. Transparent or translucent, vitreous to pearly, a bit less vitreous than quartz. Those are feldspars. Carbonates, white, quite soft. They will have well-developed cleavage, and that's if they're crystalline. Of course, they could be micritic limestone, in which case they won't have any cleavage. Transparent with vitreous or iridescent pearly luster. Again, that's if it's a crystal. Translucent or opaque if it's something like limestone, as I say. But effervesces and dilute HCl, as I told you. So very, very distinctive. Hornblende. Most common amphibole. Dark green or black, quite hard, with the two cleavages, which you should be able to see, you know, to 120 degrees or so. It's translucent, or actually looks mostly opaque, and vitreous, although it's not very vitreous. But when you're looking at it a little bit and you poke at it, you'll see it's vitreous. And then you'll be able to say, hey, this is like hornblende, or one less familiar amphibole, possibly. The pyroxenes, also green, black, and hard. These have two cleavages at 90 degrees, as you know, and otherwise look pretty similar. But, yeah, little black things. And the micas are very distinctive. You'll see little platy, shiny inclusions in the pottery. Sometimes these are very common in some pottery, but not in another, so that might be an important distinction between different fabric groups. And so you'll have the black-brown biotite or the white muscovite. They are soft, perfect basal cleavage, so they break into the laminae, which are flexible, transparent, translucent, very pronounced vitreous luster when you're looking at the cleavage side, of course. Magnetite is black, it's hard, it's heavy. It has part, but you won't see that. It's opaque, has metallic luster, and it loves your magnets. So it's very strongly magnetic. Won't miss that. And so those are most of the easily identified minerals that you can see in pottery broken sections. So other things you're more likely to want to characterize rather than identify. And by doing that, create the fabric groups by which you'll then go on to do petrographic analysis. So that is actually like the first thing you do in any petrographic study, although it's come rather late in the course, because, you know, you're not doing base studies. You're looking at thin sections. But if you get to do this yourself, that's where you start. Okay. Thank you.